Architectural Enhancement of Bitcoin by Group 11. Welcome to our presentation on the proposed feature for Bitcoin Core. As you may know, Bitcoin Core is a widely used software that processes around 300,000 transactions per day. However, it currently lacks support for offline transactions, which can be inconvenient for users who require the functionality. To address this issue, we're exploring the addition of offline transaction capability to Bitcoin Core. This will allow users to transact offline without having to convert their bitcoins to a fixed currency or rely on a centralized intermediary, promoting decentralization and enhancing security. When considering adding a new feature to the system, we took into account the principles of object-oriented programming. Creating the new features as a module has benefits for adding, removing, and maintaining it. Therefore, with the addition of offline transaction as a feature in the system, there have been changes to the current conceptual architecture that affects the communication between the new module and a series of existing features. After discussions and a SAAM analysis, a new subsystem was added to the conceptual architecture to accommodate the offline transaction module. Adding an offline transaction feature to Bitcoin Core would have involved transactions with several existing components. Here is an overview of how the offline transaction component would interact with these components of Bitcoin Core. 1 UI, 2 wallet, 3 validation, 4 crypto, 5 storage, and 6 node networking. The first implementation designs an offline transaction module that generates QR codes, signs, and scans transactions. This module interacts with the wallet feature for private key management and balance updates. The validation feature confirms transaction validity, while the crypto feature signs transaction data securely. The storage feature handles an additional metadata. Signed transactions are automatically broadcasted to the network. This implementation involves the use of an OOP architecture style, where each layer has its own set of responsibilities. The hardware device is responsible for cryptographic operations, while the Bitcoin core system handles communication and wallet management. The separation of concerns promotes modularity and makes it easier to maintain and update the system as a whole. The alternative implementation designs an offline transaction module that uses dedicated hardware devices for signing offline transactions. This protects the user's private key from internet exposure, as the device securely signs the transaction in its own environment. The wallet feature updates the balance, and the transaction is automatically broadcasted when the system connects to the network. This implementation involves the use of an OOP architecture style, where the new feature is designed to be modular and flexible. The module will interact with features talked before by defined interfaces. This implementation enables code responsibility, easier maintenance, and faster development, as objects can be developed independently and tested in isolation before being integrated into the larger system. In order to offline transaction functionality on a Bitcoin core, building a new feature offline transaction and connecting it with the original system by OOP architecture, it is a great approach of implementation which benefits for adding, removing, and maintaining it. It brings some new dependencies. UI dependence on offline transaction. Offline transaction depends on node networking, wallet, validation, storage, and crypto. Potentially impacted system. To let the whole system interaction work generally with a new feature enhancement, we believe that there are 5 submodules inside offline transaction that will have dependencies on other modules. Offline transaction generation depends on wallet. QR code generation depends on offline transaction. QR code generation, and QR code scanning depend on each other. QR code generation depends on offline transaction generation. QR code scanning scans at the generated QR code. Transaction signing depends on wallet. Transaction signing depends on crypto. QR code scanning depends on validation. Transaction broadcasting depends on node networking. And transaction broadcasting depends on transaction signing. Thank you.
Thank you, Ryan. Let's talk about the SAM analysis. First, I want to talk about the different non-functional requirements that are important to each stakeholder group. Let's start with the users. Usability is a key for users. They want to be able to implement new features easily and without hassle. They also want to be able to detect the effectiveness of new features they implement. Additionally, users want to know if their cryptocurrency wallet is private and protected from hackers, and that the offline transactions are secure. For the developers, on the other hand, are focused on maintainability, reliability, and testability. They want to ensure that their software is easy to maintain and extend in the future, and that it doesn't experience frequent crashes or interruptions. They also want to be able to test their offline transaction module with different cases to ensure its quality. And miners need scalability, efficiency, compatibility, and reliability. And exchanges and wallet providers require security, compliance, and interoperability. Lastly, investors want transparency and security in terms of information and protecting their investments. Maintaining and evolving software is important, especially when adding an offline transaction functionality to Bitcoin Core. There are two approaches. The first involves adding a new offline transaction module while maintaining majority and well-documented codes. The second approach uses dedicated hardware devices, but may require modification to support different devices and firmware updates, increasing maintenance burden. The first approach integrates offline transactions indirectly, while the second approach integrates it directly into the Bitcoin core. What main limits is adoption and evolvability. Comprehensive testing is necessary for both approaches, but testing the second approach may be more challenging. Implementation 1 requires less development time and capacity and has lower hardware requirements, making it the preferred choice. It can handle offline QR codes, signatures, and scanning of transactions. In this use case, we propose a way to conduct secure face-to-face Bitcoin transactions using the offline QR code transaction enhancements and add a new components which name is offline transaction module. The process involves the merchant requesting offline face-to-face transactions through their user interface, and offline transaction will generate a QR code which contains their wallet address. The customer scans the QR code, inputs their transaction information, and sends it to the wallet component. The transaction is then signed offline using a cryptography library and encode into a QR code for the merchant to scan. The bulk process is complete in offline environments. Once the signed transaction is verified, it is broadcast to the Bitcoin network, validated, and added to the BlockChain like a standard Bitcoin transaction. This approach ensures secure data transmission and a seamless transaction experience for both the customer and the merchant. This is a sequence diagram of our second use case, which demonstrates the significant role of hardware wallets in ensuring secure and efficient offline Bitcoin transactions. By employing the offline transaction module in the hardware wallets, users can safely initiate transactions without the needing of internet connection. The process involves the user connecting their hardware wallet to a compatible device and entering the receipt address and transaction amounts through the user interface. The hardware wallet then calculates the transaction details, sends the transaction, uses a cryptographic library, and generates a signed transaction QR code. The user can then scan the code using a separate device with internet access, and the compatible wallet application, which broadcasts the transaction using the API and RPC and the PD and the CM components by leverage hardware wallets. Users can eliminate the risk of exposing the sensitive information to the internet and conduct secure and efficient offline transactions. The offline QR code transaction enhancements combined with hardware wallets provides a robust and secure framework for Bitcoin transactions. To test the offline transaction module in the Bitcoin system, we need to follow a series of steps. Firstly, we must set up a separate testing environment to avoid any crash. Secondly, we need to test the module functionality by conducting various transactions offline. Thirdly, we need to test for security vulnerability to ensure the system is not compromised. Additionally, we need to test for regression to make sure new code and enhancement do not break existing functionality. Finally, we must test for integration to ensure the offline transaction module works coherently with other modules in the system. Adding an offline transaction module to the Bitcoin system can introduce various risks that can impact the security and the stability of the system. Those risks include the network synchronization issues, malicious actor attempting to steal funds or disrupt the network, the risk of double spending, unconfirmed transactions, and the challenges with the key management. Proper attention and measures must be taken to address those risks and ensure the security of the system. Thank you so much for the listening.